macro transport processes. Today he's going to talk to us by different subjects, the confessions of the closet natural philosopher. Howard?
Well, thank you very much. Like Professor Adamson, I would like to add my words of thanks to Tom Ford and Carol myself for their help in organizing this and for their prodding to get all the manuscripts out from the various people who are contributing to the Kenwood lecture. Now, despite the fact that the title of the talk today seems to be different than the talk that I gave several years ago, as many of you know, as you grow older, all talks have a way of merging together and becoming pretty much the same talk, so don't be surprised if some of the macro transport shows up here by way of illustrating the theme that I'm going to be discussing with today. It would help if you would have an opportunity to read the abstract, but I assume that many of you have not done that. What I have observed in recent years, particularly among chemical engineering students, I won't speak for chemistry students, is the onset of a disease that is going to be of epidemic proportions, which relates to the use of supercomputers. And since I hold a doctor's degree, I thought it was appropriate that I could name it, and I've named it non-skeptis supercomputitis. And it relates to the non-skeptical attitude that is engendered in young people by their enthusiasm for supercomputers and all the wonderful things that it can do. I don't want to give a negative talk, and as much about supercomputers that is very valuable, and among other things, a very nice attractive features is the remarkable graphics that it produces. And a particular feature that I would like to identify that I believe is of particular interest to people in the colloid area is the fact that supercomputers are capable of extraordinarily rapid and hence exact calculations in which one has some theory, and that where one previously couldn't do the computations on that theory because it was too complicated, but supercomputers allow the possibility of performing these calculations. And since students are taught that the aim of science and indeed engineering is to seek exact answers, then it's very natural that they follow this route in attempting to describe problems exactly. And the difficulty in that philosophy is the fact that supercomputers, by producing extraordinarily detailed information, produce what I refer to as microscale information, whereas human beings are normally used to thinking at a much coarser level, macroscale thinking. And the microscale and the exact thinking are synonymous, and what we're talking about is something that's coarser and hence in some sense more approximate, but nevertheless is what human beings are used to thinking in terms of understanding. And I've taken an example over here, a hypothetical example that might come from statistical mechanics. It involves a lot of things moving around like colloids suspended in fluids. The idea is that we've now reached the stage where one can actually track in time and space the motion of a fairly large number of particles, perhaps not 10 to the 23rd yet, but nevertheless significant numbers of particles, statistically significant. And one can project into the future that the numbers that can be handled will increase, and consequently that's a good thing, or so it would seem. As you know, the object, or at least the fundamental object of describing the motion of molecules, and I'm thinking of molecules in the gaseous phase, is the idea of using Newton's laws of motion to calculate the velocity and the position of every single body in there, this being the ith particle and being 10 to the 23rd of these particles. at some instant of time t. So the game is one has n particles, one gives the initial velocities and positions of all of these particles, that represents the input time t equals 0, and one applies Newton's laws of motion to follow the particles in time, and we assume the particles interact through some potential which depends on the position of each of the particles in the system. And hence, starting with initial conditions, Newton's laws of motion and non-potential, then it's a well-posed problem, and in principle, then one could calculate the velocity and the position of each particle I at time t. And so now we imagine a student 10, 20, 30 years down the line, whenever we can handle large numbers like this, who naturally has a specialized education. Of course, progress needs always to become more and more specialized. The student then is an expert in programming. That's his field. He's a chemist, he's a statistical chemist, and he's able to write very good programs that very efficiently can handle larger numbers of particles. And he starts out with all particles in some state and follows their motion in time, and he is able to tell you exactly what the position and velocity of every single particle in that system is at every single instant of time. So he knows exactly the state of that system, precisely. And of course, he's very pleased with that information, and then he runs into an old timer who is not used to supercomputers and remembers the old days when we could only do those problems in principle. We couldn't actually do them in practice. And he says to this young man, that's very interesting. He says, what is the pressure of the system? And the young man says to him, I never heard of that concept. He says, why are you asking me that question? I know everything there is to know about the system. There's nothing further I could know about the system. And the person insists that he must know what the pressure is. And the young man is curious, and they enter into some dialogue, and he says, all right, well, tell me what you mean by that. And the old-timer explains it in physical terms, but that's not, it's all very vague and so on, and the student insists that he explain it in quantitative terms. And so finally they reach a state where the old person is able to produce some formula that enables him in principle to produce the pressure from the given data in the problem, in particular potential, and perhaps other things. And the young man is astonished to discover that somebody believes in this thing, and that there is such a pressure, and particularly it's independent of time, for example. And it's independent of initial conditions. And so what he does just to humor this person, he goes ahead and he takes all of his exact data at different instances of times. He follows the rule that's been prescribed for calculating this, and indeed he produces the same number all the time, at least within some fluctuation or some small approximation, and he's astonished that there is such a number that categorizes the system. The point that I'm trying to bring out then by this simple example is that while it's true that the young man knows everything there is to know exactly about the system, in a sense what he knows is not terribly useful. In addition, there are things that are true that are not contained in the numerics of the thing. For example, that the result ultimately, that there is this number that's a collective property and ultimately becomes independent of time, for example. So what I'm suggesting is that there has to be some balance between the exact calculations that one is capable of performing and macro-scale concepts. And I think it's very important that that point be made with young people. I would like to illustrate this in a little more quantitative terms by just pulling out some slides that were left over from my Kendall Ward talk some time ago, macro transport processes. Hopefully not all of you have heard the talk, or mercifully you've forgotten the details and it will look new to you again. But the basic problem that it was addressed follows this idea of coarse graining in relation between exact and approximate solutions. The picture that we have drawn here in the basic physical problem is we have the Poiseuille flow of a solvent in a capillary tube of radius or 0. And the fluid is flowing at some mean velocity v bar. It's just the average velocity is Poiseuille flow. And as you know, the flow is a parabolic flow with R0, the radius of the tube, and R just the distance from the center. One introduces some solute into the flowing fluid and is interested in how the solute distributes itself in the fluid, how it's convected, and how it undergoes diffusion. And one knows that the exact description of the transport of the solute in here is through a transport equation, which I'll call a microtransport equation. It's just the basic convective diffusion equation for the transport of the solute. The solute is carried by the fluid velocity, that's the convective term. It diffuses with diffusivity d according to Fick's law, and this then is the equation that describes the transport in time. So that describes the exact problem, the micro-transport problem. The boundary conditions are no flux at the wall of the tube. The solute can't get out of the tube, and then one gives some initial condition. Initially how you introduce the solute into the flowing fluid at 0 time. This then becomes an exactly posed problem that one couldn't ordinarily solve analytically, even though it's a pretty simple equation. The complexity of the velocity field precludes simple analytical solutions, but certainly on a supercomputer or even a lesser scale computer, one could solve this problem numerically. And if that's what one is interested in, then one is all done. One has an exact description of the problem in which you now know what the solute concentration is at every single point in this tube, every single radial position, every axial position z along the infinite tube, every angle phi, and at every instant of time. And the information would be overwhelming, the exact information. In addition, it's recognized that normally one is only interested in the area average concentration in the tube. And so one can produce this area average concentration by this exact microtransport solution done on a supercomputer. And then if that's what one wants, one is done. The point of view that we adopt is that if one is only interested in the average concentration, which is a coarse-grained quantity, in fact, there may be some other simpler way of solving it. And in fact, G.I. Taylor, many years ago, showed that the average solute concentration C itself obeyed a convective diffusion equation, where U star was the mean velocity of the solute in the tube, and D star was something that he called the dispersivity, which is not quite the molecular diffusivity, but is related to it. And he showed that the coefficients that appear in this one-dimensional or macro transport equation, that not surprisingly, the mean velocity of the solute is the same as the mean velocity of the fluid, and that the dispersivity consists of the sum of a molecular term plus an interesting term involving a mixture of convection and diffusion. And we won't go into the details of this because we're really only interested in the philosophy of this. The idea, and these coefficients are obtained by nice coarse-grained theory, but the point here is that if one wants to calculate the average concentration, you can either get it by solving the microtransport problem and then averaging it, or you can get it alternatively by solving this coarser-grained problem, in which one only has some simple, easy to understand coefficients in there as opposed to producing just numbers. And so the emphasis here is on the macrotransport processes and how it's useful to think about these quantities. And what I'm going to do is to go over several examples that illustrate the use of this concept in chromatographic processes. And in the course of doing that, we will go from looking at a whole lot of molecules, solute molecules, and concentration, to just looking at a single such molecule. We introduce the idea that we have the same physical problem. We're just going over the same problem now from the point of view of focusing attention on a single molecule or a single Brownian particle, if you will, suspended in the Poisson flow. And the molecule or the Brownian particle is carried along by the flow along the streamlines, but at the same time, due to diffusion, it wanders off the streamlines. And one has the idea of there being some probability density, that if initially you introduce the particle at this point, at some time t later, the particle will be at some other point. And one could, in principle, calculate this probability density as a function of time. And in particular, we'll be interested in what happens after a long period of time where the particle has had an opportunity to sample all the different points in the cross-section many times, and then one would hope that there would be some sort of average or coarse-grained behavior. And in order to arrive at this, one, in principle, could solve the equation for this probability density. It obeys an exact convective diffusion equation, the same equation as the C obeyed before. And one looks only then at the moments of this equation, that even though one could, in principle, solve it, one is only interested in the moments. The first moment is just one that represents the conservation of the particle in there. The zeroth moment, rather. The first moment is just, the first axial moment is just the mean displacement from the original position in the direction of the flow. The z coordinate minus the z prime coordinate, the average value of that. This is the definition of it. And one can prove in this coarse graining process that in a long time limit that this grows linearly with time. And the coefficient then defines the mean velocity of the particle down the tube. The particle is sampling different fluid velocities at different points in the cross section. If you wait long enough, it will reach on average some mean value. And the mean value that you get is exactly the same as the mean value of the fluid velocity, which is not surprising because in a sense this particle behaves no differently than a molecule of a fluid. That if you look at a molecule of a fluid, it wouldn't be moving along the streamline, but would be sampling all the different points in there. And so one gets this result, and then one also gets the second moment, Einstein-type result, where the mean squared displacement about the mean position goes linearly with time, and one gets a diffusion-like a phenomena or a dispersion-like phenomena. And so the idea is that the fine scale or exact problem corresponds to probability density, but we're only interested in two measures of this, two coarse-grained measures, mean velocity and dispersivity. And the idea now is to apply the concepts to some rather complicated problems in chromatography. In particular, if one, suppose we look now not at a point-sized Brownian particle, but a finite-sized Brownian particle of some finite radius A in the tube of radius R0. And as the particle moves down the tube, it will also undergo all of the sampling. And one is able to work out the macrotransport theory or the Taylor dispersion theory to find out what is the mean velocity of the particle down the tube as it samples the different positions. And here now one gets a different result, that the particle does not move with the mean velocity of the fluid, but in fact it moves faster than the mean velocity of the fluid. Lambda here is a parameter that depends on sphere to radius ratio. And this, the fact that the particle velocity and the fluid velocity is not the same, but is a function of particle size or the radius ratio is shown by this little graph over here. One, the particle moves with the velocity of the fluid, one gets velocities that are greater than 1, showing that it moves faster. And in addition, this is shown as a function of sphere size. The explanation for this phenomenon, the macroscopic explanation, is quite simple, and its basis, in fact, for dynamic chromatography. If one imagined that the Brownian particle was made out of glass and had the same refractive index as the fluid, so you couldn't see it, then you could identify it by putting a dot at the center of the particle. And one sees then, as the particle samples all the different positions in there with this black dot, that because of the finite size of the particle, the little dot cannot get to the wall and can't sample the really slow-moving streamlines there, as opposed to a molecule of the fluid or the solvent, which can sample all the points in there. And so one understands that this particle doesn't waste its time in the slow-moving streamlines near the wall, and that's why it moves faster, that one just throws away the slow-moving streamlines here. And that's a macroscopic explanation of what's going on, and while in principle all of that information would be contained in the exact solution to some specific microtransport problem, the simplicity, the understanding would somehow be lost in the numerical detail, or one wouldn't even choose to seek it. And this is the basis for chromatography. If you put in 3 different size particles, a mixture of them, then the larger particles would exclude more of the slow-moving streamlines. They would move faster than the next size. They would move faster than the next size, and they would all move faster than the fluid. And so if you put in a mixture of such particles, one would achieve a chromatographic separation in which the larger particles move faster than the others and move faster than the smaller ones. And of course there would be a dispersion also, non-sharpness of the separation. Another example of this, simple example, would explain affinity chromatography. We're back to point size of particles. The particle now has a tendency to be adsorbed on the walls of the tube. And as if one writes down the microtransport problem, then the boundary condition that is imposed is a linear Henry's law isotherm relating the surface concentration to the bulk concentration of the wall with a Henry's law constant in here. And one finds in this situation that the particle tends to sample, because it's absorbed near the wall, only the slow-moving streamlines more frequently, and hence the particle moves more slowly than the fluid. And I see my time is nearing an end over here. And so there are other examples of this macrotransport thinking that time does not permit me to go over, but will appear in the written version of this. And just to wrap things up here, the final slide tries to illustrate this by the old concept of not being able to see the forest for the trees, in which the trees represent all the detail, and it represents a microscale view of the phenomenon, and the forest, which is the broader view, represents the macroscale aspect of this. I thank you very much for your attention.
The next paper is co-authored by J.C. Chang. It was given